worries. Okay, so we're going to finish complete the sections today and start local homology. But to go back to what we've done before, maybe it makes sense to remind you the notations. So what we were doing at the end of the previous lecture, we was considering the situation where we have ideal that is generated by several elements, m elements that sits inside another ideal m. Well, of course, for our applications, n is a maximal ideal inside some regular local ring S. But to formulate just general constructions, we just can consider one ideal which is sub-ideal in n, this is in the ring S. So again, in this situation, we introduce several maps. So we introduce map lambda that was called the exterior algebra of the S module n. To the m, the causal homology for the sequence y of coefficients of the S module I. We choose two free resolutions with the S module I and the S module n. So this is three resolutions. And then using these three S resolutions, we can look at the diagram where you have causal complex for the sequence at the elements A, causal complex for the sequence Y. Here we have maps alpha and beta, which is just on the first term of the causal complex. This is identity, and for the second complex, this is the augmentation map, and this is for the map beta. We just switch around the role of the first and the second complex. So first augmentation map, and then identity on the second causal complex. So here, of course, we have just the map to the product of resolutions. Well, by general properties, by the lifting, we know that there is a map from this complex to the resolution, from this causal complex to the resolution G. And we can take it as a product. And finally, another two maps. This is resolution. Again, identity of the first term and the augmentation map of the second term. So this is for the F and the same for the G. So this is the diagram, and the maps, I think last time I called this sigma with tilde and rho with tilde, right? This is map from the complexes, and the corresponding maps from the homology, this maps induce some maps from the homology. I'm going to go with the same letter, but without tilde. So you maybe fix this, that the rho will be a map from the homology of the causal complex of the sequence A, with coefficients in the S module n to the door over ring S, with coefficients in the S module I, S module n. So this is the rho, and finally map sigma sigma is from the causal homology for the sequence Y, coefficients S module I, take values in the door with arguments S module I, S module N. Okay, yeah, I hope this is correct. Okay, So that was the notation, and then with this notation, the last thing that it proved, I'm not going to prove this again, so there was the statement that the row with the index L is minus 1 to the L, sigma L, lambda L. So of course this is for any L, so for any component of the map, right? So of course here, I mean, they have this map, and it makes sense to, so this is with a bullet, it makes sense to plug in any integer number. This will be just on the, say, the h0, h1, up to the door 0, door 1, etc. But now this makes sense. So this is the identity. Now from this identity, we can quite easily derive the following theorem. So let two sequences that we have, y and a, be S sequences, which is our situation that we're interested in when we discuss complete interceptions. Right, so in that case, this will be the maximal ideal in the regular ring, so it's generated by a regular sequence, and this will be ideal with respect to which we draw the quotient and get to complete intersection. So then we have these assumptions. So then, well, there we have a couple of isomorphisms. We have causal homology for the sequence y with coefficients in the modulo S, modulo I. This is isomorphic to the door S modulo I, S modulo M, and of course it's also isomorphic to the exterior algebra of the S modulo M to the M. So just the exterior algebra on this free module of the rank M. Okay. So this is the statement. Well, since we know that now these two sequences are regular sequences, the proof is quite easy, right? Because in this situation here, for example, we can take the causal complex as a pre-resolution in both cases, right? Because we assume that this is generated by regular sequence, so this is generated by regular sequence. So for computing these doors, we can actually use the causal complex, and hence the proof is just a simple observation that, say, rho and sigma are isomorphisms. And by looking at the previous lemma, so this statement, if these two maps are isomorphisms, then necessarily lambda is an isomorphism. Right? This is by lemma. But the isomorphism that we have in the statement is just the composition of all these isomorphisms that we have, right? So that's a quite simple observation. We have the lemma. Okay, so finally the theorem that I promised, I think last time, maybe even before that, a quite famous theorem. So this is due to Tate and independently.
Can you repeat this proof of the previous theorem?
Sure. Well, with the previous theorem, I'm just saying that since we know that this regular sequences, right? So in this, so this is any resolution. So this whole computation makes sense for any resolution. I can take causal complexes as resolutions.
Yes.
Okay. And then for the causal complexes, clearly we will get isomorphisms. So we have here isomorphisms on homology, from this definition. And then we use lemma since we have, this is the quasi-isomorphism, right? So this is quasi-isomorphism. In fact, it's even, I think it's even the isomorphism of complexes. We can conclude that lambda is also an isomorphism. Right? This is by lemma.
Yes.
So this is isomorphism, decomposition is isomorphism, hence this has to be an isomorphism. So this gives us this part. So for example, this allows us to identify this homology with this answer, but also using again resolution, Kaskazoo resolution for this sequence, we get this thing. Okay, so Tate-Asmus theorem, two independent papers. So the statement is the following: let, as usual, R and M be a local Noetherian ring. So then the following four conditions are equivalent. Following are equivalent. So first, R is a complete intersection ring. So the second condition is that if we look at the Kazoo algebra of R, this is isomorphic to the exterior algebra of the first Kazoo homology of R. Okay. Condition 3. The Kazoo algebra of R is generated by H1 of R as a graded ring. And 4, the last one, that the second Kazoo homology of R are equal to the first Kazoo homology squared. Do you have questions about the statement?
Four means.
Oh, it means that, so this is the degree 2 part of the algebra. It means that any element in the degree 2 part is an element from here. So this will be just the sum of the products, say xi, yi, such that x is in the first degree and y is in the first degree. Okay. Well, in the proof, first of all, we know that the Kazoo algebra doesn't depend if you take the completion. So without loss of generality, let me say, since Kazoo algebra of R is isomorphic to the Kazoo algebra of the completion of R, without loss of generality, we can assume that R is complete in this statement, and also that we can write a minimal presentation.
Did we prove this statement? It is?
Yes, it was this one.
Yes.
Yeah, it was proved last class. I remember that. And we also asked a question about the proof. So it should be in notes. So I'm going to the complete rings and I just choose minimal presentation for this proof. So then let's go from 1 to 2. This is quite simple proof. We try to compute Kazoo homology, which is Kazoo homology for the sequence y, well, just with coefficients r, but of course r is the same as s modulo I. And here we just look at the previous theorem. So then this is exterior algebra to S modulo n to the. So this is by previous theorem.
Why is there a degree n?
The degree what?
The S quotient n to the power of what?
M,
No, it's M.
the same M as before.
Oh, yeah, I just see M, sorry.
This is M. So this was easy because we actually proved this independently as a previous theorem, and for that we need this long lemma. The rest, the 2 implies 3, and 3 implies 4. I want to say that this is clear, right? There's nothing really to prove here. Just one statement is just a special case of the previous one. So of course the non-trivial thing to prove in this statement is that 4 implies 1. So this is where we need to do something. Okay, so in this case we know that what I called map sigma, this is an isomorphism. Right? That is because we have this situation where this is a local ring. So the second ideal that I call n, is generated by regular sequence y, which is the regular sequence of parameters in this case. So sigma will be an isomorphism.
Yeah. Why we know that R is equal to S modulo I?
Well, I assume that I have a minimal presentation.
Well, if it's not complete intersection, why we have it?
Well, the same reason. It has nothing to do with complete intersections. You always can obtain. Well, the reason that we have a local ring and any local ring has a presentation that by the Cohen's structure theorem that I discussed last time.
What?
Cohen's structure theorem.
Question.
Yeah, and then if you have any presentation, you can always go to the minimal presentation by the same procedure.
Yeah.
This doesn't depend on the whether this is complete intersection or not.
Mm-hmm.
Can you repeat why sigma is an isomorphism?
Well, this sigma was defined for the using what the resolution, pre-resolution in G, right?
Yes.
So in this case, this was called a sequence which I called to y, right? Y1 up to that. So in this case, S is assumed, of course, to be a regular ring. So because here, when I say this presentation, it means that S is regular. Right? If this S is regular, then the ideal N is the maximal ideal inside S, and this is generated by a regular sequence, of parameters.
Yes.
So hence it means that for G, I can just take the Kazoo complex, and this is just essentially the sigma is just the identity.
Yes.
Okay. So sigma is an isomorphism, and now let's look at the map lambda 2. So map lambda 2, H2 sequence F A S modulo N. H2 Y is modulo I, which is the same thing as the door 2 S or S modulo N. Okay. So this is the map lambda 2, and this map lambda 2 is an epimorphism. This is just a way to formulate condition 4. This is the same thing. So now the next step is to choose a minimal free S resolution. So let F the S modulo I be minimal free S resolution.
How is the homology of R related to what is right
So what? Homology of what?
of R in condition 4?
You're asking why this condition 4, right, is the same condition as this lambda
Yes.
being an epimorphism.
Yes.
Yeah, so do you have an answer to this question? This should be more or less clear from the everything on the whiteboard.
Well, it's kind of that we have this condition multiplied by tensor with S over N, or something like that.
Well, in condition 2, everything is S, well, everything is S modulo, but it's everything modulo N, right? Because actually you know that the left hand side and the right hand side is just vector fields over K. And K is S modulo N, R modulo N, it's the same thing. Yeah, essentially the question we are talking about is the question of linear algebra, credit algebras, not commutative algebra. There's no hard commutative algebra ingredients here. And so
Isomorphism это сигма, да? Вот изоморфизм благодаря сигма. Окей.
sure. You mean this isomorphism?
Yeah.
Yeah, this is definitely given by sigma, yes. But maybe you want to go back to the definition of lambda and look what lambda is doing. So now we can think about this H2 that I wrote here.
It's lambda 2 of S modulo N.
Yeah, but H2 is just H2 of R.
Well, but in easier terms, we can actually compute this explicitly. So what is it? Well, the lambda, if we look at what we done with the lambda, this was just an abstract of the exterior algebra of the S modulo N to the N, right? To the Azul homology of the sequence Y. So in fact, this term, we can think about this as just identify this with the lambda 2, the second degree part of the exterior algebra for the S modulo N.
That's true.
Right? So now, this whole statement is that this H2, which I can define with the torque group, but most importantly H2, well, there's a kind of this map lambda from the second exterior power of this second degree 2 power, degree 2 part of the exterior algebra, right? And I know that for the homology, this is an isomorphism. But if I look at the degree 1 part, this will be precisely H1. Right? So this is what I have here is just the kind of the H2 squared, sorry, the H1 squared, right? And this is the canonical map to the H2. So yes, this is epimorphism.
Okay, like this exterior second part of exterior algebra is exactly H2R, or what? What did you say?
It is by what we proved before. Right. Well, we proved that this is H2 for this sequence, for the Y.
Yes.
Yeah, it's a little bit different than the Kazoo algebra for the R, because Kazoo algebra for the R it will be for the different sequence. It will be for the sequence which is kind of essentially the image of the sequence which we call Y in the R.
Yes.
So it can be the same thing because, for example, the number of elements is just different.
Yes, that's true. So why you say that it's every?
Oh yeah, you're right. So this will be this is just the map for the sequence. Wait, just a second. This is for y. Yeah, for y this is fine. This is what you want.
Мне кажется, что судя по теореме, вот изоморфно внешней второй степени должно быть скорее вот второй член, как будто. Ну, судя по теореме.
Я не понял, как вы говорите, как второй член.
Нет, ну в смысле, вот вы написали то, что H2, а S фактор по n изоморфно внешней второй степени от Sn в степени m, да?
Да.
Вот. А в теореме как раз говорится наоборот, то, что H2y S фактор по I изоморфный этому. Конечно, в теореме еще есть то, что это ро изоморфизм, но...
Теорема это для Гринштейна, для Commutative
В
section.
смысле, там нельзя, да, так использовать. Сейчас, ну, просто, ну ладно. Тогда все-таки как-то получается.
Мне кажется, что это такое хорошее выражение. Сейчас надо подумать.
Можно в теореме поставить I равное N, а Y равное A.
Что поставить?
Y равное A, а I равное N.
Ну, да.
Ну тогда мы получим то, что...
Ну, мы так и делаем, да.
Да.
Честно, не понял, что мы получим.
Что H2 от ASN это лямбда 2 от SN.
Вот здесь?
Да.
Мы получим, сейчас что мы получим?
Вот это. Это изоморфизм.
Вот это изоморфизм? Да, нет, это изоморфизм мы, несомненно, получаем, да. Это, здесь у меня никаких сомнений нету. Вопрос, насколько это был другой. Вопрос был такой, что мы этот изоморфизм получаем, несомненно, мы получаем, да. А теперь у нас есть как вот это условие, что есть изоморфизм для R, да, а хочется, чтобы был эпиморфизм здесь.
А там изоморфизм или
Ну, равенство.
просто равенство?
Ну, равенство. Сейчас изучим.
У нас в время образ лямбды был что-то натянутое на пары внешних произведений. Ну,
Да.
а это и есть что-то натянутое на квадрат H1, правильно?
Да. Ну, в общем, да, раньше как это работает, просто это я хочу придумать какой формальный способ это сказать, потому что у меня получается, что вот, ну, вот есть такое равенство, да, и я из этого хочу вывести, что здесь есть эпиморфизм. Но как это правильно формально сказать?
А в чем проблема?
Ну, проблема, что мне кажется, что здесь понятно, очень все, что написано. Но просто как это формально обосновать, я вот затрудняюсь, как это формально обосновать. Мне как казалось, что это просто очевидно. Ну, так,
Я просто на самом деле то, что ты говоришь, что образ лямбда, ну, он натянут на это, на пары типа векторов из первой степени, да? Окей, это без проблем. А там разве вот, ну вот, H, ну вот, там же у нас H2, Y, S по I, а не H2R. Ну, то есть это же не совсем то, что... Ну, то есть мы же не знаем такого условия про H2, Y, S по I. Ну, поэтому я не совсем понимаю, почему это прям очевидно. Так. чакать.
Сейчас я до конца не понял, что вы можете сформулировать, что у вас именно конкретно тревожит.
Смотрите, вот что мы хотим получить? Получить, что эпи, да? Я так понимаю, эпи как раз следует из того, что образ лямбда 2 это что-то вот порожденное внешней степенью там двух элементов из первых гомологий.
Образ чего? Образ?
Лямбда 2.
Да.
Вот. И мы знаем, то, что это H2 от R, оно выглядит как просто это перемножение первых степеней. Это мы знаем. А почему мы такое же знаем для H2 от Y S по I? То есть мы же не знаем, что H2 от Y S по I, оно порождено элементами, ну вот оно также H1.
Ну, мы дано, это же H2 Y S по I, это H2 от R.
Да. Это вот.
То есть это по определению H2 от R. Или нет?
Ну, просто мы взяли же, получается, какую-то типа это как кожулевую резолвенту для S, ну там у Y с чертой. Потом потенцировали ее на R, и это получили типа кожулевую резолвенту для R. Да.
Нет, мы получили какой-то комплекс, который вычисляет как раз норм. Разумеете? Если взять тест на произведение с R.
Ну да, как будто. Они, ну это же тогда не вторые гомологии. R.
Да, мне кажется, это то сожаление, на которое я и задумался, что у нас есть как бы, то есть, ну, если надо иметь в виду, что H2, ну не 2 вообще, а какие угодно, давайте, что H для R, да, вот какие-нибудь карты, это, соответственно, надо будет взять H-карты для последовательности, ну если так чисто формально определять, то эта последовательность будет здесь, соответственно, какая? Ну, как ее обозначить, если это было у нас...
Y с нижней чертой, с верхней чертой. Тут должно быть что-то вроде образа Y.
Ну, да, ну, не знаю, может быть, так и написать, что как-нибудь вот так, да. Такой. То есть надо было последовательность Y, который порождал максимальный идеал внутри S, а это мы берем ее образ, ну, по модулю I, да. Так.
Ну да.
Так, ну, казалось бы, да, если вот эту формулу написать, то казалось бы,
Вот если мы знаем, что там умножение...
казалось бы, должно как очевидно следовать, что если мы это знаем, как бы, если мы это знаем, что мы знаем? Мы знаем, что вот если мы это сделали с чертой, то это верно, да? Тогда если мы это напишем без черты,
Ну, вообще не тривиально, там могут быть какие-то такие...
Сейчас, но мы же как бы на самом деле с чертой-то здесь это дело пишем, потому что здесь еще написали S по модулю I.
Это же одинаковые комплексы.
Нет, так, вот, нет, если S по модулю I это
Сейчас
точный функтор тензорного умножения на него, то тогда это действительно одинаковые комплексы.
Да, причем там точные или неточные?
Ну, потому что
то есть, да.
мы же не хотим к гомологии, ну, гомологии
Нет,
мы
мы
хотим какие-то.
технологию поменяем и получим ну, как-то такие, какие мы хотели.
Нет, то есть, так они одинаковые или не одинаковые комплексы?
Да, они одинаковые, да, но просто здесь вот мы написали комплексы для последовательности Y, да?
И потом привели по
Если у нас никакого экспонента еще нет, то начинаем считать его гомологией. Они нулевые просто, правда же, потому что S регулярная. Соответственно, когда мы сделаем просто произведение с S по I, мы какие-то гомологии обретаем, но какие гомологии мы обретаем? Мы обретаем ровно те гомологии, которые написаны. То есть мы обретаем ровно комплекс Кашуля, который мы называли, ну, иначе его алгебру гомологии мы называли алгеброй Кашуля для кольца R. Так что нормально.
Ну да,
Если
да, кажется,
проблем все-таки нет.
Кажется, все хорошо.
Okay, so then I want to fix this minimal 3S resolution. And just look at the two complexes. One is just the Pavlov complex, so S to the M, and the second exterior power of the S to the M. Then there is something else about it. This is will be very interesting. So this is Pavlov complex. And there is also minimal resolution. Well, this is minimal, of course, in this resolution. The first term has to be S. Then there is another term which is F1, and there is another term which is F2, something else, which won't play any role in what we're going to do. So here, this is just the same thing. Okay, so of course, as the usual lifting property of homological operators suggest, we have these maps. This one.
Wait, F it's minimal free resolution of S modulo I.
Yes.
Why you write it? To
Well,
the
I'm
S?
writing this without augmentation, so just for resolutions.
Mm-hmm.
So this
So
is
it's F0.
So there are homology here, of course. Do you want augmentation?
No, just.
So this is the free resolution. This is just Pavlov complex, and there is this map which leaves just the identity map of the S module. Okay. So
And the upper part is what?
Pavlov complex.
Of what?
Well, the same Pavlov complex as before.
For Y?
Hmm?
For Y?
Yeah, for this equals Y.
Isn't it should be N? Then like power of N.
Maybe. Just a second. So this is the minimal Fourier resolution for the S modulo I. Now I think this has to be M. So otherwise,
Yeah.
it doesn't make sense. But just a second. So this is no, but that's all right. There are no problems at all. If we have the ideal I is by definition generated by the M elements.
Yes, but you saying that this is causal complex for sequence Y, and Y is M elements.
No, I want this to be just the causal complex for the
A.
for the A. Yes.
That's
So
makes sense.
let's say this is. Complex. I just write for the ideal I. Okay. Well, yeah, sure, we have this equality in the degree 0, but also I want to say that here there's also an isomorphism. In fact, I can also write this equal modules. Right? Well, this is because how you're going to construct the minimal free resolution. Right? You have exactly in this syzygy, so what will be the kernel of the, if you have augmentation, the kernel will be just the ideal I. To cover the ideal I, you need as many generators, pre-generators, as many you have generators in the ideal. So in the ideal you have M generators. So these two things, so the beginnings kind of inside the same. Now, the third map I want to call gamma. And what happens if I look at the map gamma and then take a tensor product with K? So I want to look at this map. Module the maximum weighting. Can I identify this as with something that we already have in the blackboard?
Probably it will be lambda 2.
Yeah, that's precisely lambda 2. So this tensor product is lambda 2, which we know is an isomorphism. So now we apply the Nakayama's lemma. Yeah, so by Nakayama's lemma,
What we know is an isomorphism.
so what?
You say which we know that this
Epimorphism.
Epimorphism.
Lambda 2 is an epimorphism.
Why does lambda 2?
Well, the left part, it's definitely lambda 2.
Yes.
Yeah, that is because for the lambda 2, but there was this discussion for, that I've done it even twice for the lambda 2. There's several ways you can interpret where this lambda 2 is defined, right? So I was writing that this is the same as exterior algebra, but also we can think about this as the kind of the where was it? Yeah, we can also think about the where this lambda is defined as the precisely the Kazoo complex for the sequence A, right? For which I take the tensor product with S moduli.
Yeah, that's true, but where it's like lambda is defined as we take Kazoo complex of A mapped to the Kazoo complex of Y, then tensor product with S of Y and take homology.
Yeah, so this was the definition of the lambda, yes.
Yeah, and the left part is equal. It's nothing.
What was that part?
Like the left part, the source of lambda 2
Yeah.
is equal. Nothing strange. But why is the main is equal? No.
You mean the target?
Target. Yeah.
So the target here is, well, the target is just the target is just the homology.
Нет, таргет, потому что там торга. Ну, потому что это тоже торг.
Почему там вообще Тор написан, что H2 от Y и SPI это Тор? Мы же знаем это.
No, we can compute this because sigma is an isomorphism.
Ну да, то, что вот нижняя часть тензорной пары с K это тор, это правда. Ну просто потому что это изоленты для R, потом мы... Ладно, а почему это, вот это отображение именно такое, как лямбда 2?
You mean it might depend on the resolution?
No, I mean just like we have two maps from the same source and to the same target, but why it's the same map? So why lambda 2 is not defined by free resolution of R? It's defined by Kazoo complex of Y.
But you agree that anyway the target will be something like this, right?
Yeah.
So, for example, I can also compute this target. Well, I also know that at least up to isomorphism on homology, I can use this resolution. Right? To compute Tor 2, I can use this resolution. So, if you want, I can say something like this. Maybe this is not precisely the lambda 2, but this is lambda 2 up to isomorphism, which is another what I want to do.
Why is the target is so?
Well, the target for the lambda 2 is this thing.
Yes, why the target of gamma tensor K is such thing?
Yeah, that is because, well, if I look at the gamma tensor K, right?
Yes.
So then I will obtain here the complex that computes the, well, some homology, but this homology will be precisely this homology.
Yes.
So we take like gamma tensor K and then take it to homology of
Yeah.
this map. So it's homology of gamma tensor K.
Well, yeah. So we have this map gamma. We want to take a tensor product, right? And then if we take a tensor product, well, since this is a minimal resolution, right? So there is no really differential. So
Yeah,
that
that's
means I
true.
can think about this in terms of the complex, or I can think about the homology. It doesn't make much difference. Right? Anyway, so if I take a tensor product with K here, zero differential, the terms here that I will see by definition will be these terms, right? So for the second term, I know that we can identify this with this homology, right? And hence, this is the same map as lambda 2. If you wish up to isomorphism, but it's not important up to, I think some isomorphism, but I think it's not important at all, because what I want to say is that we know this is epimorphism, lambda 2 is epimorphism. I want to apply the Gayama's lemma and say that the gamma is epimorphism.
Yeah, may I say little something? Like we say that after tensoring with K, the differential in the bottom part is equal to 0. What about the upper half of this? Like, is there
No,
differential?
upper half will be just a causal complex with coefficients, right? It's causal complex for y, for I is generated by sequence A, so it will be, so the differential of course is not 0, but the homology are known.
So we still need to take homology. Gamma tensor K and then take homology
For what?
for equality with lambda 2.
Yeah.
Mm-hmm.
Yeah, this will be on the homology, yes. Well, because otherwise it doesn't make sense, the way it is defined, the lambda was defined on the homology.
Yeah, that's true. But now you want to say that gamma is epi by NAC.
Yeah, so let me just finish this sentence. So by NAC, I want to conclude that the gamma is an epimorphism.
Yeah, but as we say, that's not just gamma tensor K epimorphism. It's on homology. It's epimorphism, that's true.
Ну, why? Он же homology.
Не, ну мы потому что
Значит, вот это напряжение на К снизу будут и так гомология, а сверху будет лямбда 2 Т
нет,
с
нет.
Как?
Сверху будут только гомологии такие, потому что вот, ну, вот то, что вот мы снизу считаем, сверху считаем, это вот буквально комплекс Кожуля для A. И потом тензорим с K и берем гомологии вторые, и тогда у нас только получается вот source лямбда 2.
Ну, снизу уже...
Ну да, я на самом
дальше
деле, да,
давай,
действительно,
вот,
вот думаю, что
это
это хорошо. То есть действительно, если у нас из-за того, что у нас снизу гомологии, то там он эфеморфизм, если он эфеморфизм на гомологиях, то он эфеморфизм просто, это правда. Да. Ладно, это хорошо.
So anyway, so this will be an epimorphism. Okay, so the conclusion that I want to do from the observation that gamma is an epimorphism is that H1 for the sequence A is 0. Right. Let's discuss this last observation. So H1, well, this is sequence A, and this is the same as the sequence that generates the ideal arc. So, is it clear that H1 of A is 0? Well, anyway, so the H1 of A is just exactly the homology that we computed this term. Right?
Yes.
So by looking at the diagram, if you know that these two things are isomorphism, this is an epimorphism, can you conclude that H1 is 0?
Вообще надо сказать, то, что мы знаем то, что H1 у F, да, нулевые.
Так, почему еще думаю, нулевые?
Ну, потому что это изолента.
Да, я просто продолжаю блок про Запретинское, да, то, да, Запретинское, конечно, любые, да.
Сейчас. Ну да, ясно. Ну просто потому что у нас там, если у нас есть ядро вот этого морфизма, то это ядро лежит снизу как бы, и оно полностью накрывается F2. А вот это полностью накрывает F2. Ну, значит, и все. Да.
Да, это может такой аргумент сходить с доверенным поиском. Okay, but I'm claiming that that's enough. We finished the proof, right? Because if H1 of a sequence is 0, as homology, it means that the sequence is a regular sequence. In the case of a local, again, using this statement, I think that's the last statement in the section about Kazoo homology. So A is an S sequence. And that's the end of the proof. We prove that this is complete intersection. Okay. Maybe from here it makes sense to derive as a corollary simple observation that any complete intersection is Gorenstein. Yeah, well, this is clear, I hope, right? Because by the previous theorem we know that this is a Kazoo algebra is exterior algebra has point-correct duality, hence by the characterization of the Gorenstein rings by the Kazoo algebra, this is clear. Okay, so now let's look at I want to change notation a little bit. I want to maybe I change the notation and explain what the problem I'm trying to solve. So let me say that the Kazoo complex on some sequence X is the following thing. I look at the ring R and then I add as polynomial generators several elements F1 up to Fn. So this is for sequence x1 up to xn. So as many elements as I have in the sequence, and I assume that the degree of each of these elements is 1. So this is y.
And by triangle bracket you mean non-commutative always?
Yeah, I mean that this is kind of graded commutative. Since I put everything in the degree 1, I assume that they commute if I want to compute fi and fj, there's the corresponding sign. And for this, it extends for all the products by distributivity. So this is kind of like I generated a polynomial ring, but in the graded sense. So I can think about the Kazoo complex like this, right? I just have a given ring, and then I add several variables, as many variables as I have generators in the idea. Just the same way to describe the Kazoo complex. Here there's no new information, just notation. So the problem I'm trying to solve is the following. I give you a local non-trivial ring and ask you to give me a free resolution of the residue field. So this is the problem. If the ring is regular, you can do this easily, right? Because this is precisely the Kazoo complex for the regular sequence, regular system of parameters. But now suppose this is not a regular situation. Let's say this is a complete intersection, or maybe even something more general. You want to compute the resolution of the residue field K over R. So the idea is You start with the Kazoo complex still. It makes sense to write the Kazoo complex. It's not a resolution, that's the problem. H0 is correct, H0 is just K, but maybe there is H1. So let's deal with this problem that there is H1. So let's say H1 of R, which is the same thing as H1 of the Kazoo complex. Let's say that this is generated by some classes, maybe M classes, right? And trying to use Kazoo complex as a resolution doesn't work. In the first case, in the degree H0, you have problems. You have some homological classes. Let's call these classes, choose the basis in these classes. Let's call them H1 up to M. And we just another parameter, the number of the dimension of this vector space over K, if you wish. So now, let's introduce new complex. Let's say that this is T. And this will be, you take R, you add several variables of degree 1, as before, and also you add several variables of degree 2, and you add as many variables as you have these homological classes on the step H1. So let me write that the degree of each of the EI is equal to 2 for I between 1 up to M. Yeah, and also here we don't have just some generators, we have the differential, right? And this differential here, very easy to write. Right, so this is the formula on the generators, and then just extend by the product rule on all elements. So here on the T, you still have a generator that computes, that you can compute on Fi's as before. If you compute this on the Fi, you just get Xi. Now we added a little bit more variables, so we want to extend the differential on these variables, and I want to say that when you apply the differential, so apply the differential to the new variable EI, we just obtain the homology class UI, maybe J. So here in this formula, I is between 1 and N, and J is between 1 and M. Okay. What you obtain by this procedure?
It's like, what is it? Like differential of I, J lies in homology.
Well, here, I can take any homology class and kind of choose a representative.
Yeah,
So
but differential of I lies in English, and after and we.
no, the differential. So this is of degree 2, right?
Yes.
When I apply the differential, my differential kind of has to decrease degree by 1. At least this is here is true. So here on the right hand side, it has something has to be something of degree 1.
Yes.
So there are homology classes. I take a
degree 1 that lies in image of the.
no, I just take a say I don't know, if this is homology, say this is classes, right? You mean the image? Well, yeah. So probably it's the same thing. Homology, if this is a kernel by the image, right?
Yes.
So this will be the classes that lies in the kernel by the image, and this is just any lift that lives in the kernel.
Я просто немного не понимаю, смотри, мы когда дифференциал меняем, мы попадаем в образ. И после того, как мы отфакторизовали по образу, мы получили вот H1 от R.
Ну,
Вы говорите, что? Что? Разные дифференциалы?
Yeah. So this is kind of the extension of the differential. Before that, there's no differential because there were no such variables.
Yeah, that's true.
So I added variables, new set of variables, and I extended the differential on the set of variables, and it is enough to define only on the generators, because for other elements I use the linearity and the product rule. Okay, so the question is what I obtained by this construction. Well, I obtained the following. Let's look at the H1 of T. So what's H1 of T?
0.
Yeah, because precisely we choose the generators in a way to kill the homology classes. It's kind of the official name, kill the homology classes. Okay, so this is still not resolution, right? Because we don't know anything about H2, H3, etc. But at least there is no H1. Well, take H2, compute its homology, choose the corresponding representative classes, add as many variables as you have homology, and extend the differential. Continue this procedure. So if you continue doing this, well, we get the resolution well, let's say R modulo this sequence. Well, it's not in general you can do this procedure for any ideal, not necessarily maximal ideal. So which is called sometimes people say this is state resolution, but sometimes also people say Commutative, so maybe write it like Kazoo in parentheses. So Commutative resolution. And this kind of what's very important contribution of the Tate in commutative algebra, probably the only contribution of Tate in the commutative algebra, in a paper from the 1957, I think it's called something homology over non-Arthurian rings. So where he offered this construction. Well, there are many details you can study about this construction. It's quite interesting and quite useful in the commutative algebra. I only need kind of very small part of this. Essentially, I just need this step where I introduce T. But if you want to learn more details about this, you can find text by Avramov. I think it's called Infinite Resolutions. But essentially, it's kind of a series of lectures, and in the very first lecture, he introduces construction, and he proved these main properties of this construction. There are some details, kind of technical details, and I don't want to go into on my lectures, but you can find those, I think, almost 100 pages long. There are plenty of applications to problems in commutative algebra. It's very nice set of lectures, and also very interesting to read. But we're going to just use this little part where we have this complex T. And for example, we need this to give a definition. So definition, the second deviation epsilon 2 of R. This is minimal number of generators of the H2 of the T. So now we can see that the general way to define deviations, well, it's just you add more and more variables, you look what you get on the next step in the homology, and you can look how many generators you have there. So, let Rm be a local Arthurian ring. So then H2 of the T that I defined before is isomorphic to the H2 of R modulo H1 of R squared. Okay. Well, before we prove this, why this is an interesting statement from the point of view of the complete interceptions? Well, we can notice that we already know that this quotient is 0 if and only if R is a complete intersection, right? But number of the generators will be in the H2, that's precisely the second deviation. So the corollary that we can obtain from this is that the ring is complete intersection if and only if the second deviation is 0. So just another numerical invariant, but it's simpler than the previous one. Before we have epsilon 1 minus the difference of the embedding dimension and dimension, just 3 numbers. Here we just can equate this by one number and formulate the condition in terms of just one number, one numerical variable of commutative. Okay. Let me for shortness set K to be precisely the Kazoo complex on the sequence X. Then of course we have short exact sequence of complexes. K lives inside T, and then there is some quotient. So we have a long exact sequence of the homology for this short exact sequence of complexes. H3 of the T modulo K, then there is H2 of the K, H2 of T, H2 of the quotient, and there is H1 of the K, and then there is H1 of the T, and H1 of the T is 0. Okay. Now, I want to show that this map is an isomorphism from H2 to H1, and this map is an isomorphism. Let's look at this map in more details. So, in the T modulo K, in this complex, let's look at the degree 3 part. So here we have R to the M, and there R to the M, and this is degree 3. Then there is a map to the differential, this is to the R to the M. And this map, if you just look at the definition, so here of course there's 0, so this is degree 2 part. So this map takes Fi, so these Fi's generate this R to the M. So then in the R to the M there is Ej, and the differential is sending this thing to the Xi Ej. So from this, right? So in the quotient, of course, the next term is just 0, right? So in the next term it will be something in degree 1, but in the quotient there is nothing in the degree 1. Everything in degree 1 is in the complex K. Right? So in this quotient, if I want to compute the second homology, I just need to compute the quotient of this R to the M modulo the image of this map. So let me say that the second homology of the T modulo K is isomorphic to the K to the M. Right? And because it will be precisely the same as before. It sits in degree 2, but the computation is the same as the computation, say, of degree 0 homology of the K. The map is the same. Hence, what we have here, and this is the vector space K to the M, this is the vector space K to the M. There is an epimorphism of these maps, hence this has to be an isomorphism. So this is actually an isomorphism. So actually, the short exact sequence that we have is actually quite shorter. We have H3 of the T modulo K. Then there is this connecting homomorphism. Let me give this a name delta. I would also can use this delta here in the notation. To the H2 of K to the H2 of T. Okay. I need to also give a name. I don't know. Delta D. Maybe let me call this map here just the large D. Now let's try to understand the kernel of the large D. Well, I claim that the kernel is generated by the following elements. I take the image under the Kazoo differential of the sequence X of the Fi wedge Fj. Then the product with the, okay, I changed notation from J to Q, so let's call this EQ. And then there is U P tensor EQ. Okay, so this is the kernel of D. Do you see why this is the kernel of D? Because, of course, everything that I wrote here clearly is in the kernel of D. But why there is nothing else?
Why it's clearly in the kernel of D?
No, just by definition. Remember that this U that I wrote is just the same as before theorem. This is just the elements that represents the homology of dv1. So since they represent homology of dv1, of course the differential of the U is 0, and of course the differential of this wedge product that I wrote is 0 since the Kazoo differential squares to 0. So this is clearly the kernel, but there is nothing else.
Because in a cycle in H2
Yeah.
of key is equal to UP up to boundary.
Exactly. So it's essentially because we choose kind of basis in all the cycles, basis in the homology, right? So then there is nothing else that could be in the kernel. Okay, so we have this, and then there is a kind of computational part that I want to skip because now I need to compute what the connecting homomorphism is doing, and as usual, this is quite a long diagram chase, so I'll leave this as an exercise, that if you apply the connecting homomorphism to the Kazoo differential of the Fi wedge Fj tensor EQ, well, then the result of a computation will be Kazoo differential applied to the Fi wedge Fg wedge UQ. But you can also rewrite this using the product rule as the Kazoo differential applied to the Fi wedge Fj wedge. Okay. Well, I know. Do you like this notation or not? Because well, maybe that's okay. Yes. No. Well, yeah, I think that's okay. There are no problems with the notation. Is it clear that this formula is correct? I'll just apply the product rule and we know that the differential on the U is 0. Okay, and also separately we can compute the connecting homomorphism on the elements of the form UP tensor EQ. If you do this, the answer is UP wedge UQ. So the summary is the image of the connecting homomorphism delta is H1 of R squared. Right? Because in the homology, this doesn't give any contribution. Right? So this delta of the elements of this form in the homology is just zero because this is d of something. So the only contribution to the homology are elements of this form, but this is precisely elements that generate h2 of r squared. And I think we proved what we want, right? Because if we just look at the short exact sequence, we have h2 of t, and this is precisely the quotient of the h2 of r by the image of delta, which is h1 of r squared. And so corollary, a local Noetherian ring R is complete intersection if and only if the second deviation of this ring is zero. Is it time for the recording? Oh, it's postponed, so let's take it 10 minutes break. Я ставлю новые антирекорды. Когда я начинал курс, у меня примерно 5 страниц на лекцию уходило. А теперь я 1,5 страницы рассказывал лекцию.
Ну, вот здесь записано, как решать 13-ю или...
Ну, я не думаю, что у меня записано.
Ну, просто, если честно, интересно. Николай, а вы решили до 13-го? Нет.
Нет. Не знаю. Вот какой-то курсовой, если бы получилось все решить. 13 вообще не должно быть сложно, задуматься сложно.
Смотрите, давайте, вот у нас это, надо доказать, что у любого локального универсального кольца Гринштейнова класс модулей с конечной плоской размерностью совпадает с классом модулей конечной инъективной размерности. То есть если мы буквально нам доказать, что если мы возьмем элемент, у которого конечная плоская размерность, у него конечная инъективная, если мы возьмем элемент, у которого конечная инъективная, у него конечная плоская. Вот. Надо такое доказать. Как доказывается?
Но вы говорите, что это ясно для
конечных.
Потому что это
Да.
А как это для конечных ясно?
Но вот для конечных там тоже надо попыхтеть, так сказать.
Ну, там можно взять свободную элемент конечных, а на нее просто из длинных точек для каждого куска. Ну, мы разбиваем с этими с языками. И
Это в какую сторону?
Это из плоской, ну, из конечной свободной и конечной инъективной.
Вот. Сейчас есть конечная.
Можно было отследить просто из мысленности. Ну, это X-тор дуалити, даже нет.
Ну нет, ну понимаете, просто как бы вам так сказать, то есть там же X-тор дуалити, но мы можем сказать то, что если у n конечная плоская размерность, то у n чек конечная инъективная размерность. Ну и что нам с этого? Мы же не говорим ничего про n. То есть вот если бы было написано что-нибудь типа это, там, то, что есть изоморфизм между, там, биекция между этими классами, то это да, это нормально. Но тут же типа то, что они
может быть,
коинсайдят.
это и есть то самое место, где я неправильно сформулировал. Там сильно надо сказать, что там есть биекция между классами, то, что они совпадают. Вот.
Не, просто тогда ладно, тогда в другую сторону тоже не совсем ясно, потому что вот инъективная размерность у элемента, если инъективная размерность у n конечная, то тогда плоская размерность у n чек конечная, тогда это только тогда, когда у вас там есть у n резольвента, где каждый элемент конечный в резольвенте. Вот. А это же не для всех модулей, правда?
Да. Ну вот это как раз то место, где надо что-то поделать.
Надо для Гринштейновость, да, как-то использовать.
Да.
А это что
Ну,
ли?
там не могут не Гринштейновость, но может быть другие аргументы, что типа там если представить какой-нибудь произвольный модуль, как предел конечно пораженных подмодулей, что-то в таком духе.
Ну да, такое возможно.
А вот то, что я там сказал, что они совпадают, они объективны, возможно, вот это то, что сделал задачу сложной и, возможно, даже неправильно.
Возможно.
Извиняюсь, надо посмотреть, в общем.
Просто условия для конечных, но почти бессмысленно, потому что такая важная получается.
В каком плане?
Ну, если, например,
Я под конечным модулем имею в виду finitely generated.
Ну да, если есть инъективный конечный порожденный модуль, то кольцо арт.
Это правда, естественно. Да.
Это была задача такая, правда?
Да, там вышло.
Ну, просто я упоминал, в общем случае, это произвольная размерность, если у вас есть конечно порожденный модуль конечной инъективной размерности, то тогда кольцо у вас Homological. Ну и при этом там понятно, что как бы, его размерность то же самое, что инъективная размерность этого модуля. Это как бы такой случай размерности, который можно все-таки самостоятельно решить, гипотезу там вот эту массу, потому что я сказал, общий случай самостоятельно очень сложно решить. Поэтому почему десятилетиями.
Но она решена. Она решена.
Да, она решена. Но там есть полукольцевый способ ее решать, который я еще не успел разобрать. Но там классические способы были там вот Pavlov придумал свою характеристику P из нулевой характеристики, а потом доказывает характеристики P, то есть редукция характеристики P.
А новую в чем? Вы его не знаете вообще или нет?
Ну, новый как раз в то, что свести все теоремы, потому что существует Homological модуль, но уже не идет, конечно, порожденное. И там то же самое, то есть это доказывает сведение характеристики P, потому что характеристики больше, но да, и видимо новый способ просто состоит в том, что это сведение характеристики P можно делать очень эффективно. Это вот эта вот работа там 2016 года. Французы задумали про перфективное пространство и применение коммутативной алгебры. А там еще работа на французской написана, видимо, много причин, почему я не стал это делать. Ну, судя по тому, как я двигаюсь, у нас осталось 3 занятия. Я все-таки хотел бы провести еще один семинар по Homological, где мы посмотрим на примеры. То есть мы закончили все курсы, теперь обязательно нужно успеть локальные хронологии. Я думаю, что до конца семестра у нас локальные хронологии будут. Я думаю, что ничего другого нет смысла спешить, точно просто. Будем 3 занятия разбирать локальные хронологии, при том, что надо провести один семинар. Ну, что-то не успеем, но, наверное, не все.
Ну так я всегда, 6 включающих, вот, который сейчас будет.
Нет, сейчас будет семинар. Там просто остались долги всякие по регулярным пользам, я хочу забрать регулярные пользы, там, да, UFT.
А что там еще планировали?
Ну, там я планирую такие вещи, которые к обязательному курсу не относятся. Я хотел рассказать как раз про чуть-чуть про большие Homological пользы и как это связано с такими гипотезами социального пересечения. И второй сюжет это про всякие Гринштейнову алгебру гомологическую. Ну, просто я про него думал, мне кажется, что там за, грубо говоря, 3-4 лекции просто не удастся увидеть людей, что это хорошая толковая вещь. Там надо полноценно читать. Ну, там просто, например, книга Дорога теорема сфер, что можно характеризовать там регулярность с смыслом условий. Гомологических каких-то, то есть конечная коллективная размерность, конечная глобальная размерность, и которую по факту можно говорить просто там на К, на формулочках. Вот, может то же самое сделали Гринштейновцы. Можно ввести понятие, соответственно, что называется G-класс, ну или там вполне рефлексивный модуль. Ну, в общем, не могу дать определение, просто без специального изучения это все равно ничего. В общем, некоторые такой класс модулей, в случае, если кольцо Гринштейна, класс модулей как раз совпадает с максимальной Homological. Но можно вообще дать для любого определенного класс модулей, и после пищевой изоленты, ну, при помощи там свободных, инъективных, плоских тех, кто при помощи этого класса модулей. И, соответственно, там минимальный изоленты, это называется там G-размерности, Гринштейновой размерности. И тогда теорема будет такая, что кольцо является Гринштейновым, когда G-размерность произвольного модуля конечная, либо же просто G-размерность полевочных конечная. То есть это перенос как бы, ну просто идея такая, что как бы
ну да, как сингулярность.
Да, это потому что проективные модули, они хорошо все контролируют в регулярном случае, да? Но проективный модуль, проективная изолента, да, вот этот же класс, он как бы в сингулярном случае контролирует. И, например, можно сказать, там формулу будет называться условно Дерблиджера, это на вопрос выбора Нусбаума, там будет тоже, что если G размерность конечная, то для G размерности ровно такая же формула, через глубины. Имеется в виду. Ну, конечно, там классов модулей, где G размерность конечная, гораздо больше просто. То есть, если проективная размерность конечная, то G размерность конечная, очевидно для меня, а в обратную сторону максимальный клеймоколик, если они интересные модели, проективная размерность бесконечная, то G размерность будет просто нулевая. Вот. Ну и там из этого там очень много всякие теоретические вещи, всякие там вводить пары по обращению, с этим все связаны. В принципе, может быть, когда-нибудь, через несколько лет, можно прочитать на все эти вопросы.
Нет.
Ну что, кстати, как раз 10 минут прошло, можно решать несколько задач. So, first proposition of the vector is necessary because I think it's not very hard to prove, is that we suppose that we have a regular local ring. The dimension of this regular local ring is at least 1. Then the following are equivalent. 1, that we have elements which form a subset of regular system of parameters. 2, if we look at the classes of these elements modulo m squared, so this is in the m modulo m squared. These are linearly independent. And finally, condition 3, that if we take a quotient by this sequence, then this quotient is regular local ring of dimension d minus I. Quite standard statement. Maybe even in ATS and McDonald's there is something like this. Maybe for one kind.
We didn't prove it.
Hmm?
And we didn't prove it.
No.
Can we use some proven statements from the lecture about regular local rings?
Well, that depends what statements you want, because in the lectures this was kind of the first statement that I've stated, and it would be nice to have a proof that it depends on the statements that formulated after, because after I just was using this proposition. Yeah, I think always what you need to prove is just in the games, and just try to prove this directly.
Can I try? Firstly, if I have some sequence x1 to xi, and each is a subset of regular system of parameters. I can it is a regular system of parameters, and it means that modular m that such elements in m modulo m squared are linearly independent.
Yeah, in fact, this is just the basis of the m modulo m squared. And this is the definition.
Yes,
of
it is definition of a regular system of parameters. So we are done because it is the dimensional covector space. From 2 I can obtain 1 because I can complete such sequence to up to a base.
Why do you call this a basis? This is a basis.
A basis, okay. It means that such elements generate m modulo m squared over m modulo m. And by now, Benjamin's lemma, such elements, some their preimages generate m over r. So it means that it is a system of parameters because I have found exactly d elements and the dimension of r is d. And it is regular because the images in m modulo m squared are linearly independent. Then from 1 I can get 3.
How do you get that if they're like linearly independent, that means that they're regular? How do you get such statement?
No, regular system of
No,
parameters.
in the end of the second proof, you say that since it's linearly independent, that means that it's regular.
A regular system of parameters, because the definition of regular system of parameters is that its elements modulo m squared are linearly independent of k. It is a basis.
Okay.
Yeah, it's confusing because regular system of parameters, by definition, has nothing to do with regular sequences. It's just a system of parameters that generate the maximum this one in the regular. So, but that, of course, we proved it previously. So the equivalent between regular and the sequence, but this is just still here, not information.
Okay.
Now, from 1 to 3, I can prove by induction on pi. Take any element x, consider x1, and since we have a regular local ring, this domain, hence x1 is clearly a regular element, and
We don't know that R is the domain.
no, it is
Regular local ring.
yes, but it is
Yeah, it's the domain if you
Yeah.
prove it. But
Yeah,
we
but
will
we have
prove
proved
it by this.
no, it can be proved
It's
straightforward.
possible to prove the statement without using any statement for local rings, for regular local rings.
Yeah, but that proof that we use that any regular ring is a domain, does it rely on the statement?
No.
I don't remember. But
I know that in at McDonald it is proved without such, without considering any
No,
sequences.
I'm not saying this is not possible. I'm just don't. If I remember correctly, from this we derive something else, and using this.
Okay.
This is precisely the next statement that I don't see that we use this preposition.
Yes, we do by induction.
Yeah, so it looks like maybe this is in the time. So that's not a problem.
So x1 is a regular because R is the domain, hence the dimension of R modulo x1 is exactly d minus 1, and let M be a maximal ideal. Then I can clearly it is equal to M modulo x1. Then I have such thing, and what I only have to prove that R modulo x1 is regular. Then I have a sequence x2 and so on to x1. It is will be a regular system. It will satisfy condition 2 clearly. So I can then apply the step of induction. And to do this,
Could you just say something like M has dimension D and X1 is one element of the basis? If we
Yes.
divided
Yes,
like,
yes.
d minus 1 and something like that.
I'm going to say exactly this. Of course, I can consider, of course, the residual field is the same, so it is such thing modular and it is exactly d minus 1 because dimension of such thing is d. So we are done. And then we apply the step of induction. And finally, I need to show the 3 implies exactly 1 or 2. It doesn't matter because they're equivalent. It is an equal local ring of dimension d minus 1, so I can find such elements in squared such that they form a basis in tilde modulo m tilde square. So I can consider the pre-images and since m tilde is m modulo such thing and m tilde squared is m tilde m modulo m squared plus such thing, I get that I need some place. I get that x1 and so on xd is a basis in of course they generate such thing because these elements generate m tilde and I consider modulo such ideal. So they generate and of course I apply such thing. So they generate over k m modulo m squared. And of course they are linearly independent because if there is some linear dependence, I can take a quotient modulo x1 and so on to xi, and then get a linear dependence for these elements because it is a base. I get that the coefficients are 0. So
yeah, but you actually can have some linear dependence in the x1 xi.
Actually, I don't need. It is enough to prove that they simply generate because the dimension is d.
Yeah, just maybe it makes sense to compare this with something that you already know from the analysis. When you, from the third semester, when you study manifolds, definitely you study statements like this. You have a bunch of functions. You want to consider the zeros of these functions, and you want to understand when the zeros of these functions give you a manifold, right?
Mm-hmm.
What was the criterion when this is true?
Нам еще нужно производные взять, там, что-то там, взять, как-то там, чтобы эквивалент был. Ну да.
Yeah. So if you think about this, this is precisely this condition. condition true, right? Because when you, well, think about this is functions, right? In the m modulo m squared, oh, think about this as just a form of power series, like an example. Then in the m modulo m squared, well, if this is at the end, there is no constant term, right? So then here and this will be just the differentials, precisely the linear parts. Everything that's just in the square and is just zero. So here this is kind of like a differentials. Condition 2 is saying that you have linear independent differentials, then when you take a quotient by these functions, you get a kind of smooth subvariety or manifold in the analytic situation. So this is kind of like an algebraic version of the same statement that you already know. So in particular, maybe the simplest possible situation, I have only one function. It says that if the differential is not zero, then the quotient, no, not the quotient, but just zero, so this function form something which is smooth or singular. So just to relate this abstract algebraic statement to some geometry that you already know. Okay. So then there was this lemma in some neighborhood of the Sayre's theorem, which I think is quite easy, but let's discuss this. We have a ring, some number which is non-negative, then the following are equivalent. So first, the projective dimension of a module is bounded by m, and this is for all our modules. So to the same condition, but only for finitely generated modules, finite are modules. The injective dimension m is finite, and this is again for any R module. And for x n plus 1 between m and n is 0, and this is again for all m. Because what we were using on the lectures is just the equivalence of the conditions 1 and 2, but when you see condition 3 and 4, it's actually easier to prove. And in the conditions 3 and 4, there are hints how to prove this.
So I suppose from 1 to 2 it's obvious, and also from 3 to 4 to 1 it's obvious. Okay, so everything we need to prove is from 2 to 3. To 3. Yeah, but we have some condition on identity n. We have the following equivalent condition, and that stated something like that. Identity on n is less.
So it's not identity, it's injective.
Yeah, injective dimension on n is less or equal than n, small. It's if and only if any x n plus 1 from R modulo I to the n is equal to 0 for any I ideal in R. Yeah, now R model I is always finitely generated. It's generated by one element, the one, and that's true. So everything proved.
Yeah. So the key is to reduce everything to the barest criterion. And this is what we need to go from 2 to 3. Okay, so now let's go to the unique factorization domains. That was the question. Yeah, so maybe I need to remind you this 4-term exact sequence. We have R star, which is embedded into the Q of R. So the assumption is that R is a normal domain. So then we have the divisor map to the divisors of R, and then there is the canonical map to the classes of the divisors of R. And yeah, so show the following. If we know that the height of some prime ideal is 1, show that P is principal if and only if C of P is 0. So this is the reason why I recall this sequence and maps, not to repeat the definition of C. Because in one direction it's very easy. The question is how to use in another direction. Рисовать, так начинается сессия.
Что, завтра честно, когда
Просто я задумался, у нас там точно 3 занятия, потому что я все рассчитываю с того, что у нас 3 занятия в декабре.
Да, у нас начинается со среды или с четверга.
Ну, то есть как раз вот толстый спирт успеваем.
Да. 21 число.
Да, кстати, когда будет этот следующий лесок?
Следующий через неделю.
А,
Ну, просто я не во-первых, у меня нет 10 задач, чтобы именно по полной причине я не просто знаю, что по локальной технологии. Сейчас вообще бессмысленно, потому что через день начнем. Поэтому я думал по поводу последнего листа, вот я его запущу в следующую неделю, я по-прежнему там 3 недели, и получается, что просто два, как раз там понедельник, когда будет сессия уже идти. Но я думаю, что это небольшая проблема. После 3 недели, потому что люди стоят, время, чтобы решать это все. Ведь уже в мае, уже большей части дальше было много, потому что последний раз уже не очень нужен. Тогда план такой, в следующий раз будет 2 лекции по локальному опыту, надеюсь, что зашкаливаются. Потом будет еще одна лекция, потом покажется. По крайней мере, ну, я надеюсь, успеем дойти до локальной мощности, хотя бы будет 4 наконец, делаем семинар. И тут еще последние занятия лекции, делаем локальную мощность для формы, наконец. Если успеем, там все время есть такая интересная последняя высоко, подскольно, Лихтенбаум. Надеюсь, что успеем. Связано с моей историей. Тема связанности подсобных снимал. Я какой-то момент, кстати, пообещал анализирующие комплексы. Я попытался подготовить по ним лекцию. В общем, это не очень работает. Вот, если так наивно твоей теоретической, это нужны производные категории. Иначе оно очень странно выглядит. Ну там тест вроде работающий, но максимально странные. Поэтому на самом деле, для вообще локальной технологии лучше смотреть в контексте преодоленных категорий. Там из принципа какой смысл понятно. Ну, вот я сделал, как это принято в учебниках компьютерной делать. Но вы можете иметь в виду, что когда там будут изучать локальные технологии, имеет смысл подумать про как функцию производную категорию. Вот, некоторые вещи могут быть красивые доказаны. Реклама появляется, из этого не очевидно. Может быть, я про это рассказываю в следующую осень. Я был план читать спецкурс по 8 нескольких индиков. Показать все от начала до конца максимальной мощностью. Ну, так как это сейчас не доказывает, а не так, как это сделано в платформе, то, что делано в платформе, уже не актуально. Просто в 2016 году появилось полное доказательство. Это там вся тема перенесла на преодоление категории.
Advoicing перспективка это же вот про то, что дуализирующий комплекс, да, с этим.
Да, ну просто перпендикуляр относительно, это вопрос есть пункт такого образа.
Перпендикуляр функция, я помню, да.
Соответственно, есть там правый сопряженный какого функтора. Существование свойства этого права сопряженного, это и есть просто перпендикуляр. Ну, в частности, когда у вас все так точку, то вместо комплексов у вас там вообще какие-нибудь когерентные пучки, это называется там 8 СССР.
Да.
В общем, в курсе, где будут одновременные категории, производные категории со всеми деталями, локально много и гораздо больше смысла их обсуждать, чем в курсе по коммутативной логике. Сделано такую стандартную программу, как во всех учебниках сделано, но очень не очень нравится.
I'm going to show that if CP is zero, then P is principal. Indeed, what means that CP is zero? It means that P as an element of this group is diff from some f, where f in lies here. Since it is an effective divisor, then f lies in R, as we have proved. Then I want to show that P is generated by F.
But how do you know that this is effective? If effective means that all the coefficients that you have in your divisor are not positive, right? But if you
No, but
There's only one coefficient.
only one coefficient which is equal to.
you just apply this just for P, yeah, P definitely effective.
Yes.
Yes.
Yes, I mean that this is effective.
Yeah, P is effective, yeah.
Hence, F lies here. And I want to show that P is actually such thing. Firstly, I know that if I consider F as an element of RP, then it actually lies in PRP. So it means that if I can multiply it by some A, which not lies in P,
Why f lies in PRP?
because new P from F is 1. Hence, actually holds such thing for some R in R. But since P is a prime,
Sorry, I don't understand the previous application. If F is the maximal ideal, right, then what you're saying that FA is in the P?
No, I think
You're lifting from the localization?
Yes, true.
Okay.
and get that F, I can multiply by some sin and get into P. Hence, F lies in P because P is a prime ideal. And then, so I have shown that there is such inclusion. And then take any P, pi in P. And I want to show that it lies in, it lies here.
uniformism, yeah.
Not exactly.
Well, maybe it's just G. But
no, I would like to consider, I explain why I use this notation. This is, I want to use, to assume such thing.
So it's lifting of uniformism.
Yes, it is some lifting of uniformizer.
Well, I'm going to try to understand. You take this,
So maybe I should explain. Take any element here,
yeah. So any element that
G.
Both sides to be included in the other direction.
any element G. Then I can go to localization and G lies in P, consider it is as an element of P, Rp, and then I know that nu P from G is at least 1, because it lies here. Hence, such divisor, I can divide it by f and get an effective divisor. Because maybe there should be another prime, but since G lies in R, all other the coefficients at any other primes would be non-negative, and the coefficient at P would be also non-negative because of such thing. Hence, it lies in R, and we are done.
Yeah, may I ask, what if G localized, when we localized over P, what if G will equal to 0?
Because it is a domain.
How we know? Normal domain, yeah. Mm-hmm. Yeah, can you repeat why for any other prime the new P of G over F is less than 0, or more than 0?
Because diff G over F is equal to diff G of G minus diff of F.
Maybe you can try to think about this a little bit geometrically. You have a variety, right? You want to understand the divisor of this rational function. So you have somewhere it is 0, somewhere it is maybe infinity, right? So it's infinity potentially where f is 0. Right?
Yeah.
But where f is 0, we also know that the g is 0, maybe even with a higher order. So this is not a problem. So
Yeah.
this thing is actually effective.
Mm-hmm.
And the second statement, again, as before, R is a normal domain. We need to show that R is a unique factorization domain if and only if the divisor in class group is a zero group. Maybe it's even easier than the previous one.
Probably. I can stress. So in this direction, like the class group is 0. That means that for any p, C of p is 0. For any p such that height p is equal to 1, C of p is 0, that means that p is principal. For any p, height p is 1. P is principal. That means that R is a UFD. We had such statement in the beginning of UFDs. Okay, so in the other direction, if R is UFD, that means that for any p of height 1, C of p is equal to 0, but diff r is something like any element from.
So why are you saying that, why COP is 0?
Well, just because for any p height p is equal to 1, that means that p is principal, that means that C of p is. Yeah, okay, I can write it down. That means that.
No, just we can write in terms of Reynolds saying P is equal to something generated by X.
P is equal to x. That means that C of p is equal to 0. But any element of any, I don't know.
Well, I think you're still skipping a step, so I'm just trying to force you to explain why C of P is equal to 0. So P is principal,
Yes.
right? But how exactly you derive that C of P is 0?
By this.
Yeah, so you probably saying that you can present this P as the divisor of X, right?
Yeah, but like we proved this statement. I'm just using it.
Okay.
It's Nikolai that don't prove this the other direction, not me. Okay, yeah. But any divisor of
Yeah, but I think Nikolai didn't prove this in the direction that we usually the single direction, right? We usually that if this is principal.
yeah, Nikolai didn't prove the easy direction.
Is he? Okay.
No, he didn't.
Didn't. So
Yeah.
that's why I'm asking these questions.
But you should be asking here. Okay, yeah. Any divisor is looking like some finite sum with coefficients and pi's where all pi's are of height 1. Height pi is equal to 1. And so C of d is sum of ai C of pi, so 0. Something like that. Okay.
Yeah, and I think we have one more thing that we need to prove from this chapter about UFDs is that when we defined first general class, so essentially remember that the definition was the following. So if M distortion, we said by definition that the C1 of M is the C applied to the H of M, and if M is free, then we say that the C1 of M was 0. Well, then you can say that if you have any module, right, any finitely generated module, then you can find a free submodule. So L inside M is free, right? And then say that the Chern class of M is the Chern class of the quotient, which is a torsion module. So find the free submodule such that the quotient is torsion. But from this definition, it's not immediately clear that this is an additive function. So if you have a short exact sequence, then we need to show that the C1 of the M is the C1 of the M prime plus C1 of the M double prime.
I suppose I proved it for torsion models, yeah?
Yeah, for torsions, torsion this is quite easy.
I would like to reduce the statement to the case of torsion modules and assume firstly assume that there is some free submodule in M prime. This is free, and since it is an injection, there.
You want this to be free, such that the quotient is also torsion.
Yes, but this works. What I'm saying, it works for any free submodule. I can consider another short exact sequence. I mean, by such, I mean that we embed L prime into M. Of course, it is exact, and C1 from any.
Of course, this is exact. It's what's second homological, third homological theorem, right?
Here is clearly an injection.
No, I mean you can just say that what you use is the I don't remember the name, but this is second or third homological theorem.
Yes, but it can be seen straightforward.
Yes, it's the easiest theorem.
Yes. So it is a short exact sequence, and if I apply C1 to any of its terms, then I get the same as for this sequence.
Mm-hmm.
Hence, I can take L prime such that M prime modular L prime is torsion. And then, without losing of generality, I can assume that M prime is torsion. Then I would like to do a similar procedure for M double prime. I have suppose I have a free submodule M double prime. Then if I denote this map by phi, I can consider the pre-image of its basis and get a free submodule in M.
Why stays free?
Yes, just yes. I will explain it. It is clear because double prime is have a base such base, then I take UI in M such that phi from UI is EI, and then I claim that L by all these elements is free. Indeed, if I have some linear dependence, then after applying phi, I get linear dependence of EIs. But it is a basis thing.
Because linear dependence can sit in M prime. like you have linear dependence such that AI lies in M prime.
No, AI are the elements of the ring.
Yeah.
And if I have such thing, then the sum of the such sum is 0. And because it is a basis, then all AI's are 0, hence I have no linear dependence in UI's. Hence I can consider such a free submodule and then a short exact sequence.
So can't AI multiplied by UI sit in M prime? Can't be, yeah?
Yes, I'm going to explain it why the sequence is that.
No, I mean when you say that linearly independent, can't AI multiplied by UI sits in M prime?
It can, but it doesn't matter because if I have such, and then I can apply phi.
Yeah, you apply
To zero.
Yeah, you
And
apply
get a
phi.
zero.
And like, ну там, типа, у нас есть какие-то там AI, UI, ну там A1, U1 плюс A2, U2 равно нулю, да? A1, A2 не равны нулю, но A1, U1 лежит в M', A2, U2 лежит в M'. Там они схлопываются. После того, как мы применим фи, все это схлопнется в ноль. Слева, левая часть.
Я не понял, я доказывал, что есть
Да,
вот такие U1,
да, вот.
доказываю, что они не независимы.
Но вот пускай не независимые.
Вот, такое тогда.
Да.
Потом я применяю фи к нулю.
Да.
Вот, получаю 0.
Но у нас просто некоторые AI, UI могут схлопнуться в ноль. А до этого они могли быть на нуле.
Нет, я беру фи, применяю к этой сумме.
Да.
Это же фи, он линейный, поэтому это сумма аитов на фи
действительно.
от аитов, это вот это.
Да.
Это 0. Then I claim that this sequence is exact. Clearly, here is an epimorphism. Why? Since phi maps L isomorphically onto L double prime, and the kernel of phi is equal to M, then I get that this map is injective. And also one can see that there is exactness in the middle term. Yes. Hence, I reduce the problem to the case where M double prime is also a torsion module. And if M prime and M double prime are torsion modules, then M is so a torsion module. Because tensor by QR is preserves exactness.
It's exact, yes. Thank you. So I think that's all the next that I have about the regulants and unifactorization domains. I think the rest I've proved from the lectures. Yeah. So now let's go with the problem for complete interceptions. So I'm using the same settings as I was using today on the lecture with ideal I, N, inside S, etc. And I also want to assume that number M is the same as number N in the special case. So then show the following. Well, maybe I write this.
So R is equal to field? So R is equal to field?
No. Why it's equal to field? It's elements would be different. So the situation, maybe let me say that m is equal to n, and let me also maybe call this C, just to avoid confusion with the maximal ideals. All right, there was this problem last time. So the ideal I is generated by C elements. I'm going to call them A as on the lecture. This sits inside ideal N, which is generated by the Y's. Again, there is C of such Y's that sits inside S. So then show that if you consider the column ideal I and N, then this is equal to the I plus the principal ideal, which is generated by the delta, where the delta is the determinant of the matrix Aij. Right, so since now we have the same amount of generators in the n and in the I, when we express I A in terms of y, there will be some matrix. Now this matrix is squared, so we can talk about the determinant, and we can prove this identity.
And do we suppose that this is regular?
That S is regular. Well, I think we can do this without the assumption that this is regular, but well, I think it's a general statement. Well, if you're stuck, you can try it with the regular case. Maybe we can discuss the regular case if you can do the general. But look, I don't see that I used anywhere that this is regular.
So this is arbitrary local material ring.
Yes. Local material ring with the maximal ideal in this case n. Maybe on the next line n, but meaning that this is n, this is ideal, so I'm going to underline this n. Of course, you probably can do this without any theory at all. Yeah, the simplest and shortest solution is using something called puzzle complexes.
Он, который на столбец, да, обычно умножаем.
В смысле?
Ну, в смысле, чтобы вот получить строчку А1 на С, мы умножаем матрицу из А и G на столбец Y.
Ну, я сказал, мы раскладываем образующие по образующим. Это прямых размножить не важно, потому что детерминанты зависят от распределения.
Ну да, это правда.
Так, у нас осталось по одной минуте, насколько я понимаю. Я думаю, что заслушать еще не успеем.